Okay. Thanks much again to the organizers for inviting me. And it's a pleasure to be here and torture people with a bit of coinduction. So I'm going to discuss inductive and coinductive, essentially basics. I will take a perspective that has been implemented in the so-called Hall-based provers, so provers based on higher-order logic. But I'm going to have the presentation really be about the mathematics of induction and coinduction. I'm going to hint to how this is actually handled in Isabelle. In fact, this is set up in the way in which hopefully everybody who follows this tutorial, they will just be able to just start Isabelle and start proving by induction and coinduction, even if they have not seen Isabelle before. So I think it's really important to focus on the ideas. So it's going to be sort of proof assistant free for most part, this tutorial, but it's going to be very hands-on. So in exchange for not having to type things in real time in a proof assistant, I'm going to ask you questions from time to time to see if people are still awake. So. And also I should say that this approach, which could be roughly characterized as the semantic approach to induction and coinduction, can be made available pretty much in any verification tool. So while Isabelle implements it, this is not Isabelle specific. Now, let me start with a little bit of motivation that I have to build for myself, because I have dedicated a lot of time to this problem, so I have to sort of convince myself that my time is well spent. I'm going to try to explain why definitions are and a proper definitional infrastructure is important. So usually, when people hear theorem proving, obviously they think about tactics and or automatic methods or interactive methods for getting proofs done. But I want to focus on really the beginning of the world, which is the definitional infrastructure. And I'm going to argue that if you have the definitions right, then of course the proof development is going to be more enjoyable and more efficient. So let's get already into some examples. Let's consider, I'm going to show you some definitions, and I'm going to ask you if you think that these definitions are correct, and sometimes why they are correct. So I start with a definition of the successor function, right? So this is the usual way in which a mathematician would say, I define a function from natural numbers to natural numbers, and I indicate the behavior of this function. Nothing interesting, nothing special. Of course, both mathematicians and computer scientists are used to recursive definitions. So we have the definition of the power function here, and this is, of course, the prominent thing to notice is that this definition is recursive. And let's keep in mind the question at the top of the slide here. So, what makes a definition correct? So, as you watch each of these examples, please think about why they are correct or why they make sense, and why are they definitions? I mean, why are they nothing different from like a property or a consistent property or a plausible property? So, what makes them definitions? Okay, so we have here's another attempt to do a definition. So a function from n to n, and again, there's a recursive. There's some recursion there. So f of x takes value 1 plus f of x. You can definitely write this in a programming language. Nothing stops you from writing it, and it makes perfect sense. So of course, it depends how we interpret what we call a definition. So, what makes a definition a definition? And of course, there are different schools of thought here, but this is my favorite, and I would say the most general way to look at this. Does there exist a unique item satisfying the property that is being stated? So really, a definition is a property stated about some item, and the mathematics surrounded the logical framework, whatever that mathematics is, constructive, non-constructive, classical, and so on, doesn't matter. It should ensure that there exists a unique item satisfying that property. And if this happens, I'm happy. That is a definition for me. Now, some people may think that this is too loose, right? So they would want the definition to be something like they construct something explicitly. Others may feel that this is too tight. So maybe they want to relax the uniqueness aspect. Okay, but in general, if you accept a definition by mere existence, then there is you typically encounter some difficulties, or at least some non-trivial design choices at the time when you want to prove things about the defined item, so, or the class of defined items in that case. So I prefer to include uniqueness in. And there's another sort of idea that I would like to convey to you, which is, again, I'm going to illustrate it in many different contexts. Definitions, of course, are important. That's one idea. And second, a definition is pretty much useless unless it has this instrumental component. So not only the ontological component, which is given by this property, but the instrumental component. It should come with ways to manipulate the defined objects. So there should be some proof infrastructure that sits on top of the definition infrastructure and appears together with the definition. So a definition should introduce some means for manipulating an object, if the definition is to be meaningful and useful for productive development, mathematical development. Okay, so without more details, or with just the details that we have there, it seems quite clear that the first two are correct definitions and the third one is not a correct definition. If we don't try to give some operational flavor here, which would very quickly require us to extend these domains with some partiality and so on. So if we just apply this criteria, there exists a unique function with that property. We see that in the first two cases, this is true, and in the third case, this is false. There's no function on natural numbers with that property. Okay. Good. So now let's look at some more styles of definition. So far we have seen a recursive definition. Now let me introduce a bit of notation. So let's consider sequences, infinite sequences of natural numbers that I'm going to call streams. And I will use this notation familiar notation for consing an element at the beginning of a string. So let's consider some definitions. So let's say we define the stream of zeros. That again, there is some recursion here. So we have zeros appearing on both sides. So it requires some justification for why this would be a definition. So this is supposed to define the stream of zeros, obviously. Now let's consider another definition, which aims to do the component-wise addition of two streams. And it goes like this. It splits both arguments into a head and a tail, and just adds the heads, and then applies recursively, technically speaking, co-recursively, it applies this to be defined operator to the tails. So again, this is a correct definition for the simple reason that there exists a unique operator plus that has this property. But the justification of this is quite different from the case of recursion. So we no longer have a decreasing measure, but we have this thing called productivity. So we make sure that in this definition we keep producing elements. So we have an infinite process that produces elements that make up the result stream, while consuming the input. So all this is about sort of the internal kitchen, but in the end we get, this is really the ultimate criterion, we have a unique item, a unique function plus that satisfies this equation. And in some sense, after this is done, so after we make sense of it, we don't need to know anything else besides that equation, that plus satisfies that equation. Okay, here's where things maybe get a bit more tricky. So we have another definition here. This is another binary function called f that I don't really know what it does. But let's look at to see whether this definition is correct, whether this definition makes sense. So does there exist a unique f that satisfies this equation? We could try to reason our way again through the productivity argument. And we see that we will keep producing elements of the result. So in this case, the first element, we know what the first element is the product of the first element of the inputs. And then we go into this corecursive context, and we apply this operator plus that was previously defined. And it happens that this operator is corecursion friendly, so to speak, so is able to actually absorb the items that f is producing. So again, there's a productivity argument that in the end leads to the existence of a unique function f. Now, in the theorem provers that inspired the approach, that implement the approach I described here, all these productivity arguments or recursion or well-foundedness arguments in the case of induction and so on, they are done in the background, and you, as a user, in the end, you get back this equation, and you know for a fact that such an item exists, and you take it from there. So you no longer need to care about the exact reason why this exist uniqueness property holds. Now, how about changing the scenario, saying that we don't know how plus was defined? So let's say we have some operator plus that was defined in some way, we don't know, and then we define this f. Now the situation changes. So, of course, the context in which we call things corecursively, just like the context in which we call things recursively, matters. So in that case, we are not going to have certainty that that represents a correct definition. And in terms of the productivity argument, really, the reason is that this plus may actually require consuming more than f is able to produce. So it will sort of get stuck in trying to produce elements, which means that the result at best is not uniquely determined. So if we don't know how plus was defined, then we don't know that f is correctly defined. Yes, Gergely. And yeah, I forgot to say, yeah, I'm very happy to be interrupted with questions. So I'll take this question and then I'll take that one. Yes.
But what's this definition for? Is this some formal power series? Or?
Well, I mean, it has, yeah, you can actually do formal power series calculus using this corecursive style. But yeah, so I don't mean to point particularly to some application. It's just an example of a definition. But see Rutan's paper, Stream Calculus and Exercise in Coinduction. He does formal power series and whatnot in this style. Yes, please.
How does this show up in Isabelle Hall's meta theory?
Yeah, so I'm going to touch upon this a bit later, not exactly in this context. But what happens is that this is reduced to something that has a combinator, a non-recursive or co-recursive combinator. So there's a final coalgebra there, and this is extended with a distributive law, and all this happens in the background. And in the end, basically, so the short answer is that this is reduced to some non-recursive and non-co-recursive primitives. There's some code that does this, that does this proof.
But if I, for example, wrote plus,
yeah,
just as a definition with that type, and I didn't give it a body.
Yeah. then you would actually get an error message that Isabelle does not have enough information to validate the definition. And this is because, I mean, anyway, this gets a bit much into the details of this. We have these things called friendly operators. So Isabelle complains that plus is not friendly, doesn't know that plus is friendly, and says, prove to me that plus is friendly. It doesn't have to be that plus, but something that has this consume one, produce one contract, and then the definition will be validated. But productivity is something that we use as an intuition, is not the ultimate criterion. The criterion is really in terms of non-recursive combinators and final coalgebras. So they are all reduced to the non-recursive kernel. Okay? Right. And here's another example. This is a function that takes a natural number and produces a stream. Can somebody attempt to tell me what the function computes?
It's the, is it collapse or go back?
Yeah. It's collapse, yeah. So, right. So basically, if the argument is 0 or 1, it's going to just output a stream of zeros. Otherwise, if the argument is even, it's going to divide it by 2. So it'll keep dividing while it's even. And as soon as it's odd, it's going to times it with 3 plus 1. So obviously, we don't know whether the Collatz conjecture is true. So we don't know whether this will eventually reach 0 or 1. But do we know that this definition is correct? So this is really another point that I want to make. Validating a definition as correct, so understanding that the definition is correct, is different from understanding what the definition does. Okay, so we don't know whether Collatz is true, but we know that this definition is correct. Why is it correct? This is a combination of recursion and corecursion, right? So the function recurses by dividing the input by 2, so long as the input is even, and then it corecurses because it produces an element here. And we know that the recursive calls will eventually lead into a corecursive call. So this is a mixture of recursion and corecursion. And yes, it is. This is a desirable infrastructure, allowing to write such combinations, such sound combinations of recursion and corecursion. But again, we have to be very careful because the recursion, while leading to a corecursion call, should not do too much corecursive damage, because we may not be able to recover from it. So this is not guaranteed a priori to be correct. In this case, it is correct, but there are some certain checks to make sure. But in any case, long story short, this function computes the Collatz function. So if the Collatz conjecture is true, then the result will always finish in zeros, in the stream of zeros. And yes, there exists a unique function f that satisfies this property. Okay, so I have already addressed these questions. So in all these questions, in all these cases, we can answer this positively. And indeed, Isabelle is happy to confirm that this is a correct definition. And if we don't have enough information, then this definition cannot be validated. Okay, so let's consider some other examples. Now with a slightly different flavor. So let's define some sets. So this is, again, a plain definition. We define the sets of even numbers, right? So no problem with this definition, no recursive definition. How about this definition? So we define this subset A of n by some rules, right? So 0 belongs to A, and for all n, if n belongs to A, then n plus 2 belongs to A. Is this a correct definition or not? For most of the people, how many people think it's a correct definition? Okay, so then I would assume that most people are undecided. How many people think that is not a correct definition? Okay, many people don't have a take on this. Yeah. So yeah, most people would say, yeah, of course, yeah, this is the correct definition. This is the definition of the set of even numbers, right? Because there's a lot of implicit, there are some implicit assumptions there. And part of what we're going to explore are these implicit assumptions and the different ways in which we can interpret. How about this one? So I only changed one bit there. I said, now the rule says, the second rule says, if n does not belong to A, then n plus 2 does not belong to A.
Does not turn on.
Sorry?
There's something missing. The second is an element there.
Yeah, that's fine. Yeah, that's how I want the example to be. That's my example.
But you said does not belong to A.
Right here.
No, n plus 2 does not belong to A.
Oh, sorry. It's my example that I read wrongly. Yeah, this is the slides are right. I was wrong. Yeah. The slides are always right. I'm often wrong. So is this I guess asking yourselves whether this makes sense as a definition is related to the question of why does this make sense as a definition? So why does 2 make sense as a definition? This is similar to the corecursion situation, but more familiar in a way. Yes, please.
2, you're defining a set.
Yeah.
Effectively.
Yeah.
But in 3, I don't think it is. It's not it's only not an inductive definition.
Yeah. Makes sense, but so how, and what do you mean by inductively?
I mean, in 2, you obviously have some base element that
Mhm.
goes in A.
Mhm.
You have a rule to kind of construct more elements from that base element. But in 3, we have a basic element of A, which is 0. But then the second bullet point, we can't combine with the knowledge that 0 is in A in order to do anything. Like, we don't actually know anything else that's in A.
Right? Yeah. But even if you knew, let's say we had a rule, let's say we had this rule as well, this bullet point as well. Would this be okay? Would this make it a definition? So let's modify 3 by adding the second bullet point of 2 as well to 3.
I don't think it would be that.
Right? So when you say inductively, and when most people say inductively, they think of a process that converges, right? So it's like, of course, strictly speaking, it's like the smallest set closed under those rules. You have a process that converges. You keep learning new elements into the set. But here, there is a problem. Because you don't have this monotonic convergence. So even if it happens by some hack that there exists a unique set A satisfying this, or there is a smaller set A satisfying this, or similar kind of rules, this is not intuitive, and it's less likely to be a fruitful definition. Because you kind of, you stumble, right? So you try to figure out that more elements are in the set, and now you are trying to infer something from an element not being in the set. But then maybe that element will be inferred of being in the set, which invalidates your previous reasoning. So there's a deep problem with this definition.
Andrei,
Yeah, please.
logically speaking, that's just saying either n is in A or n plus 2 is in A. Right?
Right. So if you think of this, yes, you kind of, if you put it like this, it sounds like a harmless property, but not really a definition. So yeah, you put it like this, and you no longer think of this as a process. You no longer think of this as the smallest set with this property. So yeah, you would make an argument that there exists a set satisfying these properties. Yes, that's correct. Yes. So that's the friendly way to look at this. But as soon as we try to look at this as a process of producing something like the least set with this property, then we are in trouble. Yeah. All right. Okay, so how about this one? We define a set of streams by saying that the stream of all zeros is in A, and if x is even, and we have a stream already in A, then we can const that even number. This looks like a correct definition, right? What does it define? What does A contain? Yeah.
And then you have like 2 appended to zeros.
Oh, you mean you think of A as a tree? Yeah, okay. I mean, as a set of streams. But yeah, I would rather think of the property of the streams that are in A. So what is the property? You only add.
So a finite number of even numbers and then zeros.
Exactly. So if you think of this inductively, then you get a finite number of even numbers and then zeros. These are the elements of a defined inductive. Good. Right. So, of course, the question: does there exist? Just to conclude our discussion, does there exist a unique set A with that property? The answer is no, except for in the first case. But we want to be more specific. So think of this as inductive definition, which most people do. We can make sense of that as a definition. So we have the notion of inductive definition, which again is an exist unique property, but it's slightly more sophisticated. You prove that there exists the smallest item with a certain property, and that item is immediately seen to be unique by the properties of partial orders. Okay, so being more specific and adding the keyword inductive, that those definitions turn out to be correct, except for the one that does not, that sort of contradicts itself in a sense, if we think about it as a process. Okay, but of course, when we are dealing with infinite data, there are different readings, there are different interesting possible readings, and in this case, the coinductive reading of the definition is also quite interesting, and we're going to delve into the coinductive interpretation of things. So that function can be, that set can also alternatively be defined coinductively. Okay, so why do we care about studying definitions in details? This is there's a list of clear desiderata that we have about the definition. So we want them to be rigorous. So yeah, we can in principle write them down in a proof assistant fully formally, correct, meaningful, and readable. And a surprising amount of work is actually put into the definitional mechanisms of proof assistants. So what most of the users of whole-based systems call definitions, they're actually properties that have been obtained after a lot of proof development that happens in the background automatically from a high-level user specification. And we're going to actually delve into some of these. So, yeah, my main point is that good definitions are the key to being productive when you're doing proof development. It's really about starting with the right foot, defining things at the proper level of abstraction and so on. So, yeah, a little bit of the sort of part of the motivational part of the work. So there are all these proof assistants out there with these nice logos, and we see these achievements that make the news, like verifying an entire operating system kernel, or proving a major theorem such as Gödel's incompleteness theorem, and or verifying an entire browser. And many of these developments, or all of them, they actually rely heavily on a powerful definitional infrastructure in order to be feasible, for these efforts to be feasible. So these are proof assistants. Well, most of you, all of you probably are familiar with what a proof assistant is. But for me, essentially, these are the main components of a proof assistant from a theoretical or logical perspective. They offer facilities for definitions and proofs, and they should allow us to get what we want really quickly at the level of definition, so that we can focus on the interesting bits without having to struggle with putting the definition in the right format. So we should be able to express things as directly as possible via definitions. So, for example, in this collapse example, we should be able to mix freely recursion and corecursion. And the definition should, ideally, we should do them at the right level of abstraction, as I said. So here's one example that I encountered quite often. There are some discussions on the mailing list about these things. for various proof assistants. So somebody wants unordered trees, but if the proof assistant only offers ordered trees, nesting things like lists, then sort of you start with the left foot. So you basically change the notion of equality, of tree equality that you are dealing with, and you carry this with you all throughout the proof development. So you would like, ideally, to define unordered trees directly as a data type. But we don't want productivity to actually, the productivity goal to impair soundness, obviously. So if you are able to prove false, if you can get the definition wrong, you are going to be extremely productive, but you're not going to prove anything useful. So it's equally important to keep definitions consistent. So and this brings actually a very interesting and never-ending research goal, finding a sweet spot into between high expressiveness and guaranteed bulletproof consistency. So, for example, we want to make sure that, as I said, that the mixture of recursion and corecursion is sound, and there are different ways to make sure that a sophisticated, that a fancy, high-level definition is sound. I would distinguish the syntactic check approaches. So, for example, in some of the definitions that I showed, you do a syntactic check to make sure the definition is productive. So you see that there is a const there, and there are two elements or one element that gives the next item in a stream. So you have this kind of syntactic checks like guardedness and positivity in the case of induction. And these are useful, and we use them in our intuition, but they are, if they stop there, if they are not backed by a semantic processing, they are error prone. So if you introduce a bug in the syntactic check, if there's no further guardian there, then the definition is inconsistent, so you sort of introduce an inconsistency in a proof assistant. The other approach, again, in reality, these two approaches, in practice, these two approaches are mixed, are the so-called semantic reductions that I already hinted at. So you make sense that everything that is not plainly definitional, right? So have these plainly definitional things. You introduce an entirely new thing, and you say A equals, and on the right-hand side, you give something that has nothing to do with A. That's a plain definition, and it's easy to make sense of that definition that is correct. Perhaps it doesn't model what you want to model, but it's definitely correct. And then you have these sophisticated recursive and inductive definitions, which are typically the ones defining interesting concepts. And the semantic approach reduces the recursive and inductive definitions to, perhaps via a lot of work, perhaps the background definitions look actually uglier, but at least they are consistent. And in the end, you prove the desired high-level property. So this is a semantic approach. It's compiling any recursiveness and inductiveness into some kernel of that does not contain any of these dangerous items. And the proof assistants actually usually take a combination of two approaches, and the proof assistance based on higher order logic, including Isabelle Hall, is quite adamant about following the semantic approach all the way to the end, so to speak. Okay, so hopefully before the end of my talk, I will get to now it's the overview about what I want to talk about. So I will show the foundation of coinduction. I will probably, based on my speed, I will not get to recursion. So I will teach. I will get into the induction and coinduction foundations of proof assistants based on higher order logic. But again, the development is not bound to a particular proof assistant. So hopefully everybody, regardless of their favorite proof assistant, will be able to relate to this example. So let's get started after this warm up with the various definitions. let me just introduce some notations and conventions that bring me a bit closer to higher order logic. But again, so I'm not going to use any particular higher order logic technicalities. Just the usual notations here, the functions notation, the lambda notations, which are all familiar with, currying. One specific, I guess, if we are to identify something specific to higher order logic that is not in the usual repertoire of working mathematicians, let's say, is this identification between terms and formulas. So we have the type of booleans, and we have predicates that are just functions to bool. So for a predicate, we sometimes regard it as a function, but sometimes just say that it holds, right? So by holding, we mean that the predicate value is true. And there's this implicit identification. We just move back and forth between these. And we're going to work mostly with, in our examples, with unary and binary predicates. But this applies to n-ary predicates as well. What's happening? This is the end of the introduction. Right. So let's get into the foundation of inductive predicates. Again, many of the things that I'm discussing here you will recognize as familiar. You may actually identify a few new things. One of the things that I noticed, because I'm kind of obsessed with infrastructure. So I mostly work on infrastructure. Other people are doing interesting developments and they just get things done. They don't care too much about the infrastructure so long as it works. And people are often mixing, let's say, the routine aspect, something that is sort of general purpose, and it's true about all the inductive definitions or all the coinductive definitions, with the interesting bits, which are like the specificity of the definition. And hopefully, sort of the usefulness of this tutorial will be to help distinguish this. So what is sort of what theoreticians call abstract nonsense, something that comes with the inductive definition, and the rest, which is specific, and for most of you, it's the interesting bit. But mixing these things brings unnecessary difficulties. So hopefully I'm going to separate them clearly in this tutorial. So let's start with some inductive definitions. We have already seen this. This is the predicate that defines a definition of the even numbers. And, well, a question that probably most of the people don't ask themselves, but why does this capture the notion of even numbers? How can we be sure that if we define this inductively, we capture the notion of even numbers? And of course, we can do this by example. We can just this is sort of the testing approach. So we can prove that even of 4 holds, but even of 3 does not hold. And it turns out that, these questions are in some sense follow from sort of the abstract nonsense of the definitional of the inductive mechanism that comes with the inductive definition. But of course, it's typically useful, especially for people who just start doing inductive definition, to come up with an alternative, perhaps more banal definition, like the direct definition of even numbers. And it's a useful exercise to actually try to prove, in a few cases, that the inductive definition captures sort of the closed form direct definition. Okay, so let's consider another example. So we have lists over an element, a set A. We use we have the usual notations for lists, the cons and the empty list, and so on. And we have this. We define this binary relation on list inductively by some rules, and I thought it's a typo, but it's not there. So we have three rules, right? So R of empty and the list S holds. And then we have two more rules. One of them allows us to add to const an element on the right. And the other one allows us to const the same element on both the left and the right. So what relation is this? Just to check that you are still with me. What does this define? Sorry?
Palindrome?
No, it's not doing any reversal of any kind. It's just simply adding, here we have empty versus anything. Here we allow to keep adding things to the right. And here we allow to add synchronously to the left and to the right. So we add more things to the right, right?
Is that just prepending?
It's more than that. It's like you allow like shuffle sublisting, right? So you get the relation where the left-hand side is a sublist of the right-hand side, where sublist means possibly skipping elements, right? But preserving the order. Okay? And we do this by saying that, yeah, we can. We start with nothing here, and we can put anything here, and then we allow ourselves to keep adding elements on the right without any match, but also to match, right? So we'll always have a sublist on the left. Okay. So we get this sublist. I think sometimes it's called a subsequence relation, and this is the way you would define it if we didn't have induction at your disposal. So you'd say that, oh, there are some indices there in the list, and the list on the left-hand side has the elements on some position. So this is one of my favorite examples showing that why we actually need inductive definitions. You don't want to work with this notion. Or even if you end up defining it like things like this, you would rather like to prove this kind of rules to manipulate things. So there's an immense conceptual step that and an immense freedom that you gain by defining things inductively. But of course, if you want to do this full journey and to be sure that you have the right thing, and it happens many times that I defined the wrong thing and I just ended up proving a lot of useful lemmas about the wrong concept. Ideally, what you want to do, you want to define this inductively, define this alternative, prove them equivalent, and then you are free to focus on the inductive definition. That's the kosher way to get things bulletproof. Because the inductive definitions, they have a simplicity that can deceive. And the coinductive definition, they are even worse. And I hope to illustrate that. But nevertheless, the simplicity is very important in proofs. Okay? And the question that I'm going to answer is, from this inductive definition, how can we prove various things? So again, a definition is useless unless it's instrumental, unless it comes with mechanisms for getting things done with a defined concept. So questions like how to prove that A is a sublist of AB and that AB is not a sublist of A, they are sort of important pragmatic questions once a definition has been produced. And of course, as I said, the various equivalencies with alternative descriptions. Now, of course, I'm going to use this notation, which is more familiar to computer scientists. So this is just another way to write these rules, but I'm going to give labels to the rules so that I can refer to them. All of you are familiar with this style of defining things. So this is the same definition, but with labeling the rules. Okay. So we have this other example now. Notice that I shifted from lists to, for need of a better name, I call lazy lists. So these are either finite or infinite sequences. So either lists or streams. Okay, so these are lazy lists. So they can have finite or infinite lengths. And now we have the same relation, essentially the same rules now, but for lazy lists. And we have this inductive definition. And I think, Gergely, you already pointed out when we were defining this, I gave that example with the streams, a list containing streams of even numbers, that if you try to approach If you try to define meaningful concepts about infinite objects inductively, you are typically not going to go anywhere. You are not going to define what you want. And in particular, here, inductively, we don't define the actual sublist relationship that we would expect on lazy list. Okay? So what relation do we define here? Well, notice that the rules force the left-hand side to be finite. We start with nil, if we think of this inductive, right? We start with nil, and then we keep adding at most one element to it. Okay? So this is definitely not relation, not the sublist relation that we want. Okay? So I already gave the answer to this self-posed question. Okay, so the inductive definition is not what we want. We want a coinductive definition. This would be in the second part of the tutorial. But now we are going to explore the inductive definition. Just as a note, as a sort of a warning sign, when you see double arrows, one typically means a double fraction lines. One typically means the coinductive definition. So when you say this is defined by the following rules, typically means inductive, but if you see these double lines, it means coinductive. What I prefer is to write specifically, explicitly inductive or coinductive, rather than deal with traffic signs like this. Right, so now I'm going to make these notions rigorous. So let me go into a little bit of the boring stuff that I would suggest that everybody goes through at least once in their life. This is really paying off. Even if it sounds like sort of a lot of ado about not much, about nothing. This is actually paying off. So this is the foundation. It is extremely simple. It is sort of deceptively simple. The foundation, the semantic foundation of induction and coinduction. So it's all about lattices and partially ordered sets. So we have a notion of a partially ordered set, and it automatically induces a notion of greater and smaller and greatest and least, right? So that's all very clear. And for a partially ordered set, we define for a subset of a partially ordered set, we have the notion of the set of lower bounds. Those are below all the elements of the set. We have the infimum. I often find that it's actually helpful to think about these things as actual intersections. So imagine those things are sets, and imagine that is a set of sets, and imagine that this is an intersection. And there are actually some theorems that back you up with that. So if you think in terms of sets, you are not really losing generality. So we have the infimum, which is the greatest element of the lower bounds, and similarly, we have the upper bounds and the supremum, which is the least element of the upper bounds. And if we have a complete lattice means that infima and suprema of arbitrary sets exist. Again, think of the set of the power set. That's the paradigmatic complete lattice. Okay, and I have some for those of you who happen to not be very familiar with these concepts. I have a lot of details on these slides, everything that is needed in order to make sense of induction and coinduction. Now, some crucial concepts. The notion of a fixed point. Okay, so you have a function on some set, an endo function from A to A. A fixed point is an element that is left unchanged by f, right? So A is such that f of A equals A. Prefix point, if we have an order on A, means f of A is smaller than or equal to A. And postfix point, A smaller than or equal to f of A. And fixed point means prefix point and postfix point, of course. Monotonic, a function is monotonic if it preserves the order, and so on. Now, the crucial theorem about induction and coinduction is a very simple theorem that is sort of can be easily understood by a high school student. The Nasto-Tarski fixed point theorem. And the short version, which is the misleading version in my opinion, because it doesn't tell us anything useful, is that any monotonic function on a complete lattice has a least and a greatest fixed point. Okay, so there's an operator on a complete lattice, and there exists a least and a greatest fixed point. But this doesn't tell us anything about induction and coinduction. I'm going to explain soon. Here is the long version that actually delves, maybe it is a bit too much detail, but it's certainly more useful than the short version. So here, this long version indicates how this least and greatest fixed point are built, which is, how to say, it's interesting. So the least fixed point is actually taken, is the intersection of all prefix points. And the greatest postfix point is the union of all postfix points. So this immediately suggests that we are focusing here, for the construction of the least fixed point, we are focusing on prefix points, which the short version doesn't tell us at all. But the prefix point, the fact that this least fixed point is actually the least prefix point, this is the heart of an inductive definition. If it were just the least fixed point, it will not enable anything interesting. So it's actually the least prefix point. This is the foundation of induction. And the greatest fixed point is also the greatest post-fixed point. And this forms the foundation of coinduction. And again, if you haven't gone through the proof, I suggest you go just once. I'm going to skip it. It's a very simple proof, but it's kind of revealing about sort of the abstract life behind this arid concepts, arid-looking concepts. Okay, so examples. The standard example again, the power set, right? So the power set forms a complete lattice with inclusion. Similarly, isomorphically to the power set, we have the set of predicates. This is actually more useful. It's more intuitive to work with predicates when you define things inductively than to work with sets. But yeah, both of them are possible and available in most proof of systems. So we have the lattice of predicates on a set A, which is isomorphic to the complete lattice of the power set lattice. And notice that we're talking about universal quantification that expresses what set theoretically is intersection, and existential quantification that expresses union. And of course, this works for any arity. So we can consider any kind of relations, and we still have a complete lattice. So it's nice that we have complete lattices everywhere, because this means that we can define things inductively and coinductively everywhere. Can I ask a question about how I'm doing with time?
30 years or so,
30 minutes left?
Yeah.
All right, good. Thank you.
5 minutes over 80.
All right, yeah, thanks.
We started a bit late.
No, it's fine. It's perfect. Thanks. So, right. Okay, so we have these complete lattices, and all we have to do in order to get inductive definitions is to define monotonic functions on complete lattice. So we don't care about any kind of continuity. The complete lattice saves us from having to have our functions continuous or anything fancier. We just want our functions monotonic, and they already give inductive definitions. Okay, so with this armed with this abstract nonsense, let's go back to the examples, the even number examples, right? So we have this even, which is defined by two rules. It's a predicate on natural numbers. And inductively means that it's the smallest predicate closed under the given rules. Okay, so you see here we have the smallest and closed under, right? So we see that we are talking about the least fixed point, but in fact it's closed under will actually mean prefix point. It's the fact that it's closed under the rules. This is really the essence of induction. So how do we make sense in terms of the Nass-Tarski theorem? How do we make sense of this definition? This is a semantic approach on this slide. So we define even as the least fixed point of some operator f, This is an operator on predicates, right? It takes a predicate and returns another predicate. How is f defined? Well, it takes a predicate p, and it returns a predicate. What does the result predicate do? I color matched here the rules, right? So it says that one of the rules must have been applied, either 0, in which case m is 0, or successor, in which case there exists an n such that m equals n plus 2 and p of n holds. So this is the operator, and this is what it does, right? So the operator actually applies the rule. So it holds for a predicate, applied to a predicate, it holds exactly for those items, m, that have been produced by applying one of the rules to items on which p holds. Okay, so, and this f is extracted from the rules. Notice here, we have this high-level specification. The user would just say, okay, I define this inductively, and now here is how the system, or us, makes sense of this definition. We define this f, we extract this from the rules. So this definition doesn't exist yet, it's just a specification. We extract this f, define, apply Nassau-Tarski and get the list fixed point of f, which it is the list prefix point, and define even to be that. So now it becomes a definition. And then we make the trip back. So we don't want the user exposed to the Nassau-Tarski theorem. We want the user to get what they have here. So we were making our way towards the semantic check, and now we are making the trip back. So we are going to infer some useful high-level rules for manipulating this concept. And we are going to do all the inference from the property of being the least prefix point, which also happens to be a fixed point. So f is monotonic. This is a semantic check that we need to do in order to make sense of this definition. Otherwise, we get into that kind of non-convergent thing, example with a negation. So f has to be monotonic, so if exists. And then we have the Nassau-Tarski theorem, which allows us to say that even is a prefix point of f, which is just this. F of even is less than or equal to even in the lattice of predicates. Yes?
Yeah, sorry, maybe I'm...
No, please, yeah.
Just read the definition. What's the ordering on the predicates again?
It's a component-wise implication. So it reflects the order, the inclusion of the sets.
Okay.
All right? So you have the implication of Booleans, and it's component-wise implication. And the intersection is for all, and the union exists. Because we want to know the whole lattice structure, yeah. Okay. All right? So, but yeah, this is actually expanded here. So what does it mean that f of even is less than or even, which Nassau-Tarski theorem gives us? Well, this is what it means. I just expanded the definition of, I should have just clicked as an answer to your question. Just expanded the definition of less than on predicates, right? And I expanded the definition of f there. So we want that, so this is basically for all m, f of m implies even of m. This is what it means f of even of m implies even of m. And this is what it means, what this inequality means. And further expanding it, we see that we split into these junctions, and this actually means that even of 0 holds, and for all n, even n implies even n plus. So what this really means, this just means that a closure under the rules. So prefix point means closure under the rules. So thinking about the trip backwards, right? So initially, these were just some desiderata. This is what the user wants. It wants these rules to hold. The system says, wait, let me check monotonicity and so on. And now I'm coming back. I proved these rules for you. So yes, you have them. Now you wrote them down, and they became theorem about something that is, whose definition is hidden. You don't care about how I define even for you. But I gave you these rules. But this is not enough, because you want the smallest predicate satisfying these rules. So you want some a proof infrastructure that comes with it. Okay, so far we are sort of halfway back with a trip from the semantic trip, so to speak. We are halfway back. We have proven these rules that the user wants. What else can we infer? Well, even is a fixed point. Okay, it's not only a prefix point; it is a fixed point. In particular, it is a postfix point. So from even we can infer f of even. What does this mean? Well, again, we are expanding this definition. So we have the reverse implication. And what we actually get is that whenever even holds, it must have been the case that one of the rules have been applied, right? So this is the postfix point condition. This is going to be crucial when we're talking about coinduction. Here is just something that happens to be, I mean, it's sort of less essential, of course very useful, but less essential. It's not a characteristic thing of even that it's a postfix point. Anyway, but about coinduction, I'm going to talk about coinduction later. So here we have this principle that says that if we know that even holds, it must have been the case that one of the rules have been applied, either zero or successor. This is what postfix point means. So a more useful way to write this, which is useful in proofs, is to put this in this format of a cases rule. So we say the way to read this is, let's say we know that even holds for M, and let's say we want to prove something called P. How are we going to prove it? Well, since it must have been the case that one of the rules was applied, we can assume that in one scenario that the zero rule was applied, so M is 0, and we prove P. And in the other scenario, we assume that M has a form n plus 2, and even of n holds, and we prove P. So this is just a rephrasing of this implication. But this is a rephrasing that is useful in proofs. And this is essentially proof by case distinction on the last, when you see this in the informal text, it's like on the last applied rule. We do a case on what rule has been applied last. This is just the postfix point condition. Finally, and crucially, even is the least among the prefix points of f. Again, it's important that it's the least among the prefix points, not the least among the fixed points, which is also true. So what this means is that for all other predicates, if those predicates are prefix points, then even is smaller than them, right? So let's expand what this means. It means that even is smaller than P for all predicates that are closed under the rules, right? So what closed under the rules means? It means that P of 0 holds, and if P of n holds, then P of n plus 2 holds. So what we get is, by putting this in a format similar to the case rule, so again, these are also called elimination formats, because it allows us to infer something from knowing that our predicate holds. This is the induction that we get, and you typically apply without giving it too much thought about sort of the abstract nonsense details about this inductive definition of M, right? So if you know that even of M holds, how do you prove that P of M holds? So notice that unlike in the cases rule, now our predicate has a parameter, essentially the parameter that we are inducting on. So how do we prove that? Well, you prove that P of 0 holds, and you prove that for all n, P of n implies P of n plus 2. If you have done this, you have proved P of n, essentially for P of m for all m. Okay, so basically this implication between even of m and P of m has been split, and even went on top of the rule. So this is the more, perhaps less intuitive, but the more proof-friendly version of the least prefix point predicate. This is sometimes called rule induction. So whenever you do rule induction on the definition of even, this is what essentially happens. Okay, so just to summarize what's happening here, how do we make sense of an inductive specification? And this is really, I mean, this is verbatim what happens in a prover like Isabelle. So with slightly different syntax. So the user writes these rules, such rules, hoping that, or having a strong intuition that they will pass the semantic test. And one defines even as the least prefix point. So the system defines even as the least prefix point of a monotonic operator that is extracted from the rules, and infers various rules from this definition, including the original rules that the user wrote. So even being a prefix point of f gives us the introduction rules that the user wanted in the first place. Even being a postfix point gives us case distinction rule. And even being smaller than all the prefix points gives us the induction rule. Okay, so this is the entire infrastructure. It's color matched here that is produced after going through this semantic trip. Right. There's a small twist that turns out to be actually surprisingly useful. You often see that induction doesn't work, and it doesn't work for a very specific reason, that it's not strong enough, not taking advantage of all the knowledge that we have. So one small twist is that we can plug in the very predicate that we are defining in the induction hypothesis here. So when you are proving that even implies some predicate, we can also assume even in the induction. So we kind of work in a closed world where even already holds pervasively. And obviously, if we prove that even is included in the intersection of even with that predicate, we have proved that even is included in that predicate. So this allows us to do a stronger induction. And this is basically the justification is that we have the prefix point of the intersection, the smallest prefix point of the intersection. So basically, this is in two steps. First, we define even at the smallest prefix point, and then we take the smallest prefix point of this operator that takes a predicate and applies the operator to even and the predicate. And this is how we get this slightly stronger, surprisingly more useful rule. Okay, so this is what most proof assistants actually add as a bonus from an inductive definition. Okay, so let's just to end this inductive bit. Let's explore a bit some of these semantic conditions. So we want the operator to be monotonic. This is crucial. So if the operator is monotonic, the induction not only that sort of we have sort of bureaucratic problems having the induction go through, but it's probably something wrong with your design if the operator is not monotonic. So it's a good warning sign. It's good that in some sense it's good that not a more sophisticated test than monotonicity takes place there. So this operator, why is it monotonic? Well, we can easily check, and this is actually checked automatically by Isabelle. It is trivially monotonic. So let's say that P is smaller than Q. We want to show that f of P is smaller than f of Q. We simply expand the definitions, and anyway, so I will leave the details here on the slides. But this is just sort of immediate processing of the connectives and the quantifiers. So this operator can be proved monotonically automatically. How about this one? So I changed a little bit. So I'm going to illustrate a few more points about Nassler-Tarski fixed point definitions by doing variations of this. Never mind the word even now, because this is not going to be the even number. We're just asking whether the definition is correct, it makes sense or not. So whether it's a correct inductive definition of who knows what. But is it a correct inductive definition? So I changed a little bit, and now I say from even of n plus 2, you deduce even of n. So now you no longer have this increase in the size of the number, right? Is this still a correct inductive definition? It is.
It just defines the set 0.
In this case, yes. In this case, you don't get any new inhabitants there. But the point that I want to make is that this has nothing to do with the size of the arguments. So rule induction works because imagine that you are building a proof tree, and we're not only going to imagine, we're going to build it in the second part. It's a proof tree, and this is the structure. This is the structure that decreases, if you want, when you apply a rule backwards. The other proof trees in the definition of the predicate. It has nothing to do with the value of the argument. It just happened that this is on natural numbers where you can also do structure induction. But this has nothing to do with the inductive definition of even. So that's a perfectly valid definition. Not of even, but of a different predicate. How about this one? We say that, so in order to infer even, we say, oh, for all m smaller than n minus 2, even m holds. And then we infer even of n. Is this a correct inductive definition? Yes. Yeah. It is because, again, it is, you see, think about, how do you think about monotonicity? You think about adding new knowledge about what's true about even, right? So whatever even means. Now we're not about even numbers. Let's be clear, okay? This predicate that is just called even here on the slides. So monotonicity really means that we keep adding new information. We know the predicate to be true for more and more elements. This is really what monotonicity means. And in this case, yes, we do. We go forward, not backwards, with knowledge. And this intuition, of course, can be checked in the sense that, yeah, you can check immediately that this is a monotonic operator, just like we check for the other. So this induces a monotonic operator. So that's a correct definition. How about this one? Now we're saying we have a bit more complexity here, right? So we say that for all m, there exists some k greater than m such that the predicate holds. And then we can infer that the predicate holds for n. Is this a correct definition? Do we add knowledge? We're playing a game here. We say, oh, for all, we have to find something. And if we find that something for which even holds, then yeah. So it's kind of like we need to find a potentially unbounded, because we are saying that there is a k greater than m, a potentially unbounded number of cases where our predicate holds. And if we do that, then we can infer that our predicate holds for yet another item. So again, it's a positive logic here. Right? So we're gaining knowledge. And you can check again that this is...
No, that's quite similar to the previous one.
It's very similar, yeah.
You can basically instantiate k to the n.
Right. In this case, yeah, the examples are a bit contrived, yes. It may be that most of these are trivial or equal between each other and so on. But try not to be too smart about what this actually happens, and let's look at the abstract nonsense, right? So we have this for all exists thing. So that definitely you made a case, Brijesh, that predicate includes this predicate includes the previous predicate, and because there's not much else to do, yeah, I think it's actually equal to it. So, but yeah, but in general, this could, I mean, you could have multiple rules here. You could have a rule that says that 180 is even, right? And then yeah, so this starts to be more interesting. But the idea is that it's okay to branch infinitely is not a problem. It's okay to have this for all exists game, or even more complex nested games, so long as we have a positive logic there. We keep adding information. Perhaps it's extremely hard to add information, but we definitely adding information. We're not going backwards. Okay, so this is also correct. So positive logic, and this can be made. Now I'm committing the sin of going into a syntactic criterion, right? So, and I'm not against syntactic criteria. It's nice to say, oh, I see that all the quantifiers here are you have for all exists. You don't have negation. You don't have implication that has even on the left. Now we're fine. But we don't stop. What I would say, we should not stop here. It's good to have this syntactic check, but this should be backed by a semantic check, which in this case is monotonicity. Okay, but syntactic checks are actually very useful. So in this case, if we stay in positive logic, within positive logic, for example, haven't included implication, has to be included in a positive way, then f will be monotonic. And this one doesn't, right? So this one is our previous pathological example, and this is how it shows up. This lack of convergence, we just cannot prove the operator monotonic. So it's kind of, this is not obviously consistent, which probably means that there's something wrong with what we were trying to define. So it's like type checking. It's like a sign that something is wrong. And this one also, right? So negation can creep in various ways, right? So you basically have the left-hand side of even also, even on the left-hand side of the implication. This also is not monotone. Okay. So I think I'm going to actually skip this. This is on the slide for who wants to check this. I'm going to skip this example with the sublists, which goes in the same way. So let me just conclude this first part of the tutorial. The semantic approach, right? We specify the inductive predicate or relation by indicating the rules that involve that predicate. This is not yet a definition. And then we turn this definition we turn this specification, this is a specification, a wishful definition, so to speak. We turn this specification into an actual definition that has nothing inductive or recursive in it. Naster-Tarski is just a property about a prefix point in the lattice. That's completely banal mathematics, so to speak. Nothing about recursion or induction. We extract the operator f from the rule. We show that f is monotonic, and then we define our user-specified predicate as the least prefix point of f. And from that definition, we infer introduction rules, a case distinction rule, and an induction rule. And the introduction rules are the rules that the user has given in the first place. Who are we and who is the system? So we, the users, write those rules. She is Isabelle in this case. So Isabelle will make sense of this specification and will actually apply these steps. It's going to extract the operator automatically and attempt to show that it's monotonic. If it succeeds, then she's going to infer all these things. So basically, the user is going to get these proof rules and this introduction and elimination rule. So Isabelle automates the things that are marked here in blue. Now, what happens if f is not obviously monotonic? Most of the times, it probably means it's not monotonic, and the definition is wrong. But sometimes, there are some things like when you are using nested, when you nest some predicates in the inductive definition, you need to help Isabelle to show that these higher order operators are actually not negatively interfering with the monotonicity. So sometimes it's actually meaningful for Isabelle to fail on a definition that should go through, and you have to help it a little bit. So you have to help Isabelle by essentially proving monotonicity yourself, giving a sufficient amount of hints so that she can prove monotonicity. Okay, so I just put some exercises here for cementing these concepts. And I think I will probably stop here, and I'm going to show how these things are actually applied for reasoning. And then I'm going to move to coinduction. And finally, I will go to this sort of unified approach, just try to put together this intuition of induction and coinduction. All right, yeah, thanks for your patience. So hopefully I'll see some of you.
Okay, so we started a bit early, but let's still come back at 3. Is that okay? We just come back at
it was 5 minutes after. Okay.
Are you not stopping now?
Let me quickly. Yeah. Sorry about that. Yeah. Sorry, I gave you hope. No. Let's take this 5 minutes just to show you because it's good actually to stop after the induction to move to coinduction next. So I'll keep you 5 more minutes. Right. So let's see how this turned into. I mean, I was talking about sort of this general purpose infrastructure for reasoning that just comes from the very definition. I mean, there's nothing creative about this. It's just sort of something standard that is being deployed that follows from the induction infrastructure. So let's consider this our running example, this even, and we have these rules. So I just collected them here. This is all we know about even, and all we ever care to know. We don't need anything else in order to reason about it. This is a complete set of properties. We no longer need to know how it was defined. So we have the introduction rules, and the cases rule, and the induction rule. So how do we prove that even holds? Which rules are we that even apply to 4 holds? Which rules are we using to prove that? So we want to prove that 4 is even. The blue ones, the brown ones, or the brown one or the green one? Just the blue ones, right? So this is direct proof. A concrete. And the way we think about this, and usually in a proof of, if you're familiar with the proof of system, this of course rings a bell. We reason backwards, so they are called introduction rules, but we think of them as being applied backwards, right? So we start with what we want to prove. We must prove even of 4, and we apply the suck rule, which is now, I kind of color matched in black. So we apply the SAC rule and reduce the fact that we want to prove even of 4. We reduce it to even of 2. And we apply again the SAC rule, and we reduce it to even of 0. And finally, we apply the 0. Okay? I don't mean to suggest that you need to do this kind of proofs by hand. Obviously, there's automation that deals with this. But for sufficiently complex predicates, you really want to roll up your sleeves and apply the rules by hand. In this case, of course, Isabelle's automation, for example, has no problem with this. How do we prove that even of 3 does not hold, or not even 3 holds? How do we prove that our predicate is not true? Blue, brown, or green? Right. So we can take this sort of this ecological approach and apply the green, but it's a bit of an overkill, right? We could survive with the brown. We could survive with cases in this case, because we keep attacking this. But yeah, both induction and cases would work here. But clearly, we're not talking about the direct proof. We're not talking about proving that even holds for something, but proving that even implies something. In this case, a contradiction. Okay? So let's apply the cases. So rephrase this statement as even of 3 implies false. And again, we reason backwards. So, and again, I'm doing some color matching here. So apply the case rule. We take M. Notice here, this is how this so-called elimination rule is being applied. We match the major premise here. Yeah, people familiar with proof theory, of course, will recognize this. We match the major premise here, and we match the conclusion. These cases and induct rule are particularly nice for being elimination rules, because the conclusion is arbitrary, so we can match anything, right? So this is the gist. So this means that we focus on the elimination aspect. We focus on what we know here. We know that even holds, right? So if m equals 3 and we take p to be false, we apply the cases rule, and we are reducing the goal to 3 equals 0 implies false. Okay, so I think I'm showing some colors here about what happens. Sorry, we are reducing the goal to 2 goals. One of them is this, right? M equals 0 implies P, which is 3 equals 0 implies false. And the other one is this, for the instantiation, right? So notice what happened there. We have used the major premise and the conclusion to instantiate our rule. And obviously, the instantiation affects the other premises as well. So now this is what we want to prove, that for all n, if 3 equals n plus 2 and even n, then false. Which is the same as even 1 implies false, right? So this is some simplification. Typically, you combine these kind of steps with simplification steps to clear this goal and get rid of unnecessary quantifications. So now we again apply the case rule, but this time for m equals 1 and p equals false, and we further reduce the goal to now 1 equals 0 implies false, again trivially true, and now this one is also trivially true, because there's no n such that 1 equals n plus 2. So we ran out of rules to apply, essentially. We keep bombarded even, and we ran out of rules to apply. Okay, so this is just, perhaps I will really stop soon. So this is just the elimination pattern. So this is, if you look closely at what happened here, I'm doing some color matching for those of you who want to take a closer look. But this is the elimination reasoning pattern, which applies to induction as well. But let me just finish with the induction. Back to our old question: why is this the correct definition of even? In this case, it's kind of obvious, but again, we can prove that the alternative closed form definition is equivalent to the inductive definition, which occasions displaying inductive reasoning, right? So when we want to prove that even of m implies that there exists a k such that m equals 2 plus k, what we're doing now we really need induction, right? So the case rule, obviously, this is unbounded. We don't know how far this is from the root, from the base cases, so to speak. So this is a case where we want to take advantage of the cyclicity of induction. So we apply the induction rule for this predicate. The existing a case such that our number is 2 times k, and this is very similar kind of reasoning. Again, the elimination pattern, just like for the cases rule, and we reduce this to 2 rules: the base case, the familiar base case, and the inductive case. And by further processing, the base case is trivial. By processing the inductive case, we easily see the witness that we need in order to discharge this goal. And of course, this is another case where automation proves this fully automatically. So both the cases and the induction introduce the elimination reasoning pattern. Now, the last point that I want to make: how do we prove such a property? It's more like a distinction that I want to make. So let's prove how do we prove the reverse? How do we prove that something implies even? What do we have at our disposal to prove that even holds? So how can we prove that an inductively defined predicate holds? We have seen how to prove that even of 4 holds, right? We apply the introduction rules. Here, this is not enough. We need something else. So this is the moment where actually induction is, or sort of an inductive definition is kind of powerless on its own. We need some intrusion from the outside in order to prove things. Now, inside the proof, we are going to apply the introduction rules. But introduction rules themselves are not enough. So in other words, the inductively defined predicates are very good at proving that they are small, at proving that they imply something. But they kind of like are powerless to prove that something implies them, unless we have trivial cases like concrete values. Yes, there was a question.
Oh, no, you kind of answered.
Okay. I detected it and I answered. Yeah. So how do we prove this? How do we prove that if for all k m equals 2 times k, how do we prove that even holds? We need to appeal to something from the outside. This is the proof. So we're going to do, this time we're going to do structural induction on k. Okay, so this is something that I haven't talked about, and this is the distinction that I want to make. There are different ways of inducting, and I essentially covered rule induction based on Nassar-Tarski fixed point. Structural induction is really, it comes with any data type, and it's about the size of the element. There is a unified view of rule induction and structure induction. If you think about the trees, if you think about the rules that actually define a data type, the rules defining even. So if you think of the trees that are proof trees for even, then we kind of have a reduction of rule induction to structural induction. If you think about inducting on the size of the tree of proof of even, as opposed to inductive on the least fixed point definition of even. But yeah, so this is really, again, something from the outside. We need to know something else about the left-hand side predicate. We need some form of minimality. It's like the smallest with some property. In this case, it's because of the minimality of the number data type. It's like the smallest set that is closed under the application of the constructors. And we play again the game, but this time with the structure induction on natural numbers. So structure induction is at least initially, unless we try to make this identification, the structure induction is different from rule induction. And another way we have sort of seen this difference is by realizing that it doesn't matter whether the values in an inductive definition are decreasing or not. So anyway, these are fairly different phenomena. And I think I'm really going to stop here. This is no longer a false alarm. And I'm going to continue with coinduction after the break. Thanks.
Okay, thank you very much.
All right. So welcome back to the co part. Now, let's get into the into the coinductive predicates. Now that we warmed up with induction. So back to our running example of sublist. Now we are in the case where we talk about lazy lists, so possibly infinite lists, finite or infinite lists. And I'm using the same notations as for lists. So we have this relation that I call sub, which is defined inductively by the same rules as before. But now, again, we're talking about infinite objects, so about lazy lists. So what do the rules achieve? This is the intuition of the list fixed point that we discussed. So everything that is provable by a finite application of these rules. Right? This is intuition. You build a finite proof tree obtained from applying these rules, and at the root you have a proof of some fact about this sub predicate. So the smallest relation that is closed under the rules, also known as the relation that is given by, that is proved using finite proof trees. And we have seen, we have already discussed that this doesn't work. This doesn't give us what we want. So we have the lazy lists, right? So this is an exercise for you, and this was pretty much what I have done when I became interested in coinduction. I was just trying to do things without coinduction. So to define a relation such as the sublist relation without coinduction. We have seen the alternative definition in terms of for induction. It already looks bad. For coinduction, well, it's essentially the same, but we're talking about infinite streams of positions and so on. That is pretty much unmanageable in terms of reasoning. So I would say that coinduction is really, in some sense, the only elegant way to define the sublist relationship. So, but let's take this easy, because now intuition kind of fails us. Is no longer clear what we mean by the coinductive interpretation. Inductive interpretation is kind of built into us. We feel induction. But for coinduction, we need to work a little bit. So induction means the least relation interpretation, right? Now, what do the coinductive interpretation means? Shall we define the greatest relation that is, instead of the smallest relation, shall we define the greatest relation that is closed under these rules? And as you would imagine, the answer is no. The greatest relation closed under these rules, it's kind of trivial. So this is not just switching from induction to coinduction. Doesn't just mean taking the largest relation that is closed under these rules, right? So is the total relation closed under these rules? It is. That's the largest relation, right? So we definitely don't want that. So we need to dualize this, but dualizing it would kind of like lose some of the usual intuitions that we have. So let's select the properties that we want. So I'm going to discover the coinductive, rediscover the coinductive interpretation and the coinduction proof rule by taking it slowly, so to speak. So let's see what are the properties that we want about the sublist relation on lazy lists. Well, first of all, we want this to extend the sublist relation on lists, right? So we want to have things like 1, 3, 4 is a sub-lazy list of 1, 2, 3, 4. And so should be 1, 2, and 1, 3, right? For infinite objects, for example, we want that zeros is a sublist of itself, just to pick some random property. We also want that the lazy list consisting of all even numbers is a sublist of the lazy list consisting of all the numbers. So these are some litmus tests. Whatever relation we define, it has to have these properties. And of course, we can spell out the exact relation that we want in this sort of closed form. So AS, we have these two lazy lists, AS and AS prime, and we want that AS prime should have this form. So it should consist of essentially the elements of AS prime, preserving the order and perhaps escaping some elements. So we have this chain of positions JP, and AS should consist of exactly those elements at positions JP. So this is a kind of trouble that we need to take when we want to define this, let's say, in closed form directly. And this would not be a problem. I mean, it can be done. The problem is that when we start reasoning about it, it's going to be very difficult. But in any case, this is the ultimate litmus test, assuming that I wrote this correctly. So we want a relation that is equivalent to this relation, whatever we define coinductively. Yes, question?
Why in the second to last line, why does J sub P need to be less than J P plus 1?
Here? Yeah, we want an infinite stream of strictly increasing positions, okay. And those are the ones that we select, and we put them in the sublist. Okay. I mean, the elements on those positions, we put them in the sublist. Okay, so that's a fairly ugly way to define this. I don't think it can be defined much less ugly without coinduction. All right, so this is what we want. So let's see, what do we retain from the inductive world? Because we retain quite a lot. So do we want these rules to be true about the sublist relation on lazy list? The same rules as we had for induction? Yes, these are intuitive rules that hold for lazy list, for lists regardless of whether they are infinite or not, right? Okay, check. How about the case distinction rule? I went more quickly through the case distinction rule for this list example, but that's, I mean, we did it for the even example, right? So if BS is a sublist of BS prime, in order to prove P, we can assume that one of the three rules has been applied, right? So that's essentially what the case says. So is it true that for not only that these rules hold, but also their inverse holds, in the sense that everything that is in the sub-lazy list relationship must have been obtained by applying a rule? Is it still true?
Not necessarily. I don't know. It doesn't feel like it should be true.
Okay, so yeah, this doesn't sound like a priori true. But let's look at the rules. Let's see what they say, right? So, is it true that if we have this sublisting, so if AAS is a sublist of AAS prime, is it true that AS is a sublist of AS prime? Yes. Is it true that nil is a sublist of any lazy list? Right. So that's actually the direct rule. I take back my question. There's nothing to say about this. Right. So I was cheating a little bit. I was pattern matching on this one. So really the question is, if we have the sublist relation between two lists, is it the case that either they start with the same element, or and the smallest lists are in the sublist relationship, or one of them has an additional element in addition to being already a superlist, or the left-hand side is nil? If you think about it, there are not other options. So we do want this case distinction. Although this is not necessarily something to be taken for granted. By the way, this is I should have made this color matching already. So this corresponds to the different rules. Okay. So these are two different ways of writing the case rule, which remember corresponds to our relation being a postfix point, right? The direct rule corresponds to our relation being a prefix point. The case rule corresponds to our relation being a postfix point. And these are two alternative ways to express this. This is the more readable way. Like, if they are in a relation, there must have been a rule that was applied. And this is the way that is suitable for the elimination style that is suitable for proofs. You know that the sublist holds, and you want to prove some P. Okay, so the cases rule should also be there. How about the induction rule? Something would have to not be there, right? So the induction rule allows us to say that the sublist relationship is included in any predicate that is closed under the rules. So as you can assume, we cannot accept the induction rule. It will allow us to disprove some of our litmus tests, for one thing, right? So it will allow us to prove, for example, something that I have already mentioned, that the sublist implies that AS is finite. So we can define finite in different ways. We can say that the length is finite. We can define finite inductively, of course, on lazy lists and so on. But let's take finite for granted. So it will allow us to prove this, which we don't want. We want to allow sublists that are infinite of other lists, right? So, for example, the zeros, this is a consequence of this fact. So the zeros will not be a sublist of itself. So the relation will not even be reflexive. We will not have the even numbers sublist of all the numbers and so on. Okay, so we don't want induction. What do we replace induction with? We're in the co world. We replace it with coinduction, right? End of story. Let's see. So this is what we have. We recover these things from the inductive world. Well, we want a proof method for infinite lists. Let's see how, in the concrete case, how do we prove something? So do you all agree that the lazy list of even numbers is a sublist of the list of all numbers? Right. How do we prove that? Here's a proof. So, in order to prove this, it suffices, thanks to the cons rule, to prove this. So what have we done? We have consumed 1, 0, right? So basically we applied the cons rule backwards. Now, what are we doing now? We are applying the cons R rule. You see again, color matched. So we apply the cons rule and we consumed one element from each side, right? And now we apply the cons R rule and we consume an element from the right-hand side. And we have reduced this to another problem. Is this problem that we reduced it, is it somehow shorter, smaller? Well, we are dealing with infinite object now, right? So in which sense is it smaller? But what we have done, we have consumed some things from the input. And we keep doing that. So this is an infinite process. We keep applying the same rules, and we keep advancing through these lists. And this is a proof. So this is an infinite proof of the fact that our list from the left is a sublist of the list from the right. Okay, so we relax the notion of proof by saying we are going to accept infinite proofs. We don't necessarily want base cases, because a proof allows you to traverse the subject items indefinitely. So we keep consuming elements from that, and you can see that nothing is left out. So this is I would argue that it's a convincing proof, but for the fact that it's infinite. Okay? So how do we make sense of this infinite proof? Infiniteness it's something kind of like at the meta level. It doesn't make sense to say that now we are going to accept infinite proofs and we're going to produce these proofs, right? So we need to be able to reason. We are going to have to apply a finite set of rules to reach our result. This is kind of like we need to work in a decidable setting. So what do we do instead? We notice what is the pattern. We describe the pattern of this infinite proof. So we produce what I would call a blueprint of this infinite proof. So do you see a pattern in this infinite proof? Exactly. So we alternate the application of cons and cons R, and we also see maybe a pattern in the content, right, of the elements. Right? So we start with this. We get rid of one, stay, get rid of another one. Okay, so we see the pattern of the relationship between this and this. So, what is the blueprint of this infinite proof? Well, you see that we are talking about the sublist relationship, but really what we care about, pairs that keep evolving, right? We pretend that we apply the sublist relationship, but it's not. It's just the content here that changes, and we want to make sure that the rules are correct. So this is not really about the particular predicate sublist. It's about any predicate on pairs, right? So, besides the pattern on the application of the rules, as I mentioned, we have the pattern on the content. So we have some relation P. We look at the relation P that exists between these items along the application of the rules. And we really have two states that we can be, right? So there exists some number k such that the left-hand side is 2k, 2k plus 2, 2k plus 4, and so on. And the right-hand side is 2k, 2k plus 1, 2k plus 2, so everything starting from 2k. There's one pattern. And the other one, the alternative one, is here we start at 2k plus 2. Here we start off 2k plus 1. So we just see what happens throughout this infinite proof. Okay? And what do we get? We get a relation, P. What happened? I didn't see what happened in the animation. We get a relation P that, what do we require from this P, from this relation P? It has to be backwards closed, right, under the rules. So it has to be the case that whenever we are in a state where P holds, there has to be a rule that has been applied backwards, and we again go into P, right? So we have the same predicate holding. So the property here, which is the case distinction, which remember it was kind of an incidental property in the inductive world. It just happened that the least prefix point, because it was a prefix point, it was also a postfix point. Here is fundamental. So the case distinction, which means being a postfix point, is exactly the property that we require from a blueprint of an infinite proof. So what I did here, I just replaced the sublist relationship with P. That's what we want from our predicate to satisfy exactly the case distinction rule for the sublist relationship. And this is the blueprint of this infinite proof. And the nice thing about this is that this becomes, by internalizing this pattern, this becomes a finite proof. So sort of I would say that a finite argument for why an infinite proof exists, right? So P, if we come up with a predicate P that satisfies this property, then we know that P is included in the sublist relationship. So this gives us the coinductive rule. So the coinductive rule in summary is a way to conceptualize, to internalize a blueprint of an infinite proof, or you could say to internalize an infinite proof. So what does the coinductive rule say? In order to prove that two things are in a sublist relationship, come up with some predicate, P, for which the property holds, and show that P is a post-fixed point of the operator defining sublist. In other words, it satisfies the cases rule for sublist. This is the coinductive proof method. Okay. Just some terminology. So we say consistent, which is another word to say that this case rule, analysis situation holds for a predicate. Say consistent with some rules to mean that it's closed backwards under the application of the rules. Essentially, the question that we addressed a while ago: is it the case that when the two lists are in or two items are in a sublist relationship, is it the case that one of those rules must have been applied? This means backwards closed. So you see, now in terms of, let's go back and say, how are we going to define the sublist relationship? We think slightly coinductively. We think slightly differently, I mean, kind of dually than in the inductive world. We don't think of like how to apply the rules forward, but you think of how to make sure that we don't miss any case. If the two things are in a sublist relationship, then one of these rules must have applied. So we think backwards. So this case distinction rule is fundamental in the way we define the sublist relationship. There's no wonder, because this is how we end up proving things about it. Okay, so just to paraphrase coinduction again, it says that if a relation in this terminology that I just introduced, if a relation is consistent with the introduction rules that are specified when given like the specification of the intended relation, then that relation is included in the sublist relationship. In other words, it implies the sublist relationship. Okay, so this terminology this is standard terminology consistent with for coinduction and greatest fixed points. Okay, so we essentially recover this greatest fixed point from the Nastatarsky theorem, but we now hopefully see the concrete intuition for why we want the greatest post-fixed point here. Because we want the larger relation that is consistent with the rules. Okay, so we have the coinduction rule in our set of desirable properties. So let's apply now the recipe. So we have this operator, which is really the same operator as in the case of it has the same shape as the operator for the finite lists. And I'm going to sort of a bit of a backwards compilation here, just to convince you that this rule that we just discovered in terms of like trying to find the blueprint is nothing but the post fixed point, being the greatest post fixed point, right? So now we plug in the definition of this operator f, and this is the coinduction rule. It's just saying that if P implies f of P, then P implies the sublist relationship. But as usual, when we are preparing something for reasoning, we put this as a major premise as opposed to placing it in the conclusion. Okay, so this is just another way of saying this. This is sort of abstractly the coinduction rule, which is just a reiteration of the fact that the predicate that we just defined is the greatest post-fixed point. Okay? All right. So going back to the general recipe, we write some rules. So when we define something by coinduction, we write some rules, thinking this time backwards. So this is perhaps not the most intuitive way to write the rules. I have just reused them because they are the ones that I used in the inductive world. But this is unfortunately current practice to which I also adhere. It's when you define something coinductively, instead of writing the characteristic properties, which is the inversion rule, the case rule, that characterizes them as the greatest relation. You write the kind of an incidental property, which are the direct rules, but you think of them backwards. So you think of the case rules that is induced by this rule, by these direct rules. But in any case, this is standard practice. So you write these rules directly, and the coinductive interpretation of these rules means greatest relation, not that is closed under these rules, but that is consistent with the given rules. In other words, so we have the greatest fixed point for an operator that is defined by taking the case expression, essentially. This is by applying the rules backwards. And again, for the same reason as before, the operator has not changed. F is monotonic, so the largest fixed point exists because of Naster-Tarski. So just to summarize, this is the recipe for making sense of coinductive definitions. We get, in this case, this subtle relationship. Being a prefix point means that the introduction rules hold. Being a postfix point means that the case distinction rule holds, and being the greatest postfix point means that the coinduction rule holds. Okay, so again, now we focused on the postfix point relationship. It just happens, so to speak, that it is also a prefix point, so the direct rules also hold. Okay, and I have some. Again, I just show the rules here. And these are, again, just like in the case of coinduction, these are the only rules that we ever care about. So this is all we need. First of all, it clearly forms a unique characterization of the predicate that has just been defined. And all we need are these rules in order to reason about the defined relation. Okay? Make sense? Any questions so far about this definition?
Actually, I have one question.
Yes, please.
Obviously, here we've extracted F fairly easily.
Mm-hmm. In the same way, right? Because we have the direct rules, just like in inductive case, and we extract F in exactly the same way.
Yeah. I'm just wondering if it's always that straightforward.
Yeah, I would say that extracting F is straightforward from the rules.
Okay.
Proving that F is monotonic may not be straightforward.
Okay.
But yeah, it's kind of a routine procedure, right? So you are looking at you just have some arbitrary items, and you pattern match against all those rules. But they don't have to be actual constructors, actual participants. You say, well, either the left-hand side is nil and the other one, well, we don't say anything about it, or the left-hand side has this form and the right-hand side has this form. So it is a mechanical process to extract this from the rules. What is, again, for me, it is a bit confusing is because the way one typically specifies a coinductive predicate does not differ from the way one specifies an inductive predicate. But it should, because that is not the characteristic property. Anyway, obviously, we can interpret this in a way that is correct. This is not invalidating correctness. Yes, please.
Related to my question, because when you were defining the peak, it looked like the blueprint looked like a cyclic behavior. Is it always going to be like a cyclic kind of?
It is cyclic. Yeah. Because the case rule is cyclic, right? So it's we do have basically the way to see the cyclicity is best to reformulate it. Sorry, it's best to reformulate it in the readable version, so to speak. Right. So this is the case rule that we started with, right? It is cyclic because it says if this is in a relation, that it must have been the case that one of the rules was applied, and one of the rules and some rules have hypotheses that involve the relation itself. Sorry, I think I interrupted the question.
No, I was wondering if you can only have a coinduction if you have this cyclic behavior.
Well, but you can only have induction, meaningful induction, if you have this cyclic behavior too. So I mean, the same situation is for induction. Otherwise, there's maybe just the rules are they have no recursiveness in them. So it's the same thing. I mean, here induction and coinduction go hand in hand. One way to sort of to explain the difference, and sort of a poor man's way of explaining the difference is that coinduction does not have the base case. It's like induction without the base case. And it is matched by the fact that you allow, you see in this infinite proof, you allow to just go on and on. So you build the same trees, following the same rules, it's just that you do not enforce the presence of a base case. They are really, for me, this maybe some people actually see the closer, deeper analogy between them. There are really two different ways to look at this. One of them is in terms of possibly infinite proof trees without base cases, and the other one in terms of this like dualizing and looking at rule inversion as opposed to looking at introduction. So for me, they are not kind of like necessarily identical, but it turns out that if you work out the details, which are not very hard, they turn out to be identical. But for me, this is a consequence of the fact that we live in a kind of a set theory, and this is the properties of the category of sets. It's not in the Nassau-Tarski theorem. Nassau-Tarski theorem doesn't know anything about this. Okay, does this? All right. So, but then I have a question for you. So we have, we did analyze the sublist relationship on lists, and we concluded that there are some properties that we do want to have, but we're not very critical about, we haven't analyzed critically whether we defined the concept that we wanted. So yeah, everything is fine. We now know how to make sense of these rules coinductively. We get this Nassau-Tarski. The operator is monotonic. Everything works, and we have our coinductive definition. But does it define what we want? Does it define the sublist relationship on lazy lists? Because we kind of imported the definition from finite lists, and we say, now let's interpret it coinductively. And we didn't interpret it like in a silly way. We said, no, we are not going to say the greatest relation closed under those rules, but the greatest relation consistent with those rules. But did we do enough? Did we get what we want now?
Yes.
All right, so you would say that this is a correct definition, and we brought some evidence for it, right? So we showed that we could prove certain things about it. We didn't show that we can disprove some things about it. Maybe we can prove too much. Maybe this is too large. This one is a possibility. And this goes back to my explanation about now we're not looking at the direct application of the rules, but we're looking at the backwards application of the rules. So in some sense, you would say that the sublist relationship is whatever survives this infinite game of applying the rules backwards. Right? So you say that two lists are in the, and you have seen this in that infinite proof that I show. They are in the sublist relationship if you can keep applying the rules, possibly ending with a nil rule, possibly not. But if you can keep applying indefinitely, and it still stays in the relation, it still survives. It is. It's kind of, yeah, it is too forgiving. So which one is the culprit? Oh, this one?
I mean,
consort. Oh, right. Yeah, exactly. Yeah. Yeah. Exactly. So we have a problem here, which is not reflecting a similar situation in the inductive world. Again, this is about our view. We look at these things backwards. So think about trying to prove that any infinite list is a super list of any list. This allows us to kick the can down the road indefinitely. We keep postponing this, okay? An infinite list has the resources to keep throwing elements and keep falling into this pattern by applying this rule. So stays infinite indefinitely. So the problem is that we can prove things that we want, but just like in our discussion of consistency, we can prove a bit too much, okay? So here's an example that the infinite list 0, 0, 0, 0 is a proof of, using this definition, is a proof of 1, 1, 1, 1, okay? We just apply the cons R rules. We are free to choose, right, which rule we apply. This is the definition of consistency. We have to say that it must have been the case that one of the rules has been applied. It would not make sense to say that all of them have been applied. It doesn't make sense in the inductive world either, right? Again, we want consistency is a concept that applies to the inductive rule as to the coinductive rule as well. We want that if a certain relation holds, it must have been the case that one of the rules has been applied. So we can prove too much. This is incorrect. We didn't define the correct definition. So this shows that basically, generalizing from finite to infinite is not straightforward because we have to think differently. I mean, it's not even generalizing. This can be a different beast. It has some similarities that I'm going to explore immediately after. But first, let's fix this. Let's fix the definition. So since you discover the problem, you have to fix it as well. Otherwise, we would have been happy. So it's really, I mean, people familiar with I don't know, the model checking and fairness properties and so on, right? So you would
Eventually makes progress, right?
exactly, and this one makes progress. The cons rule makes progress. This one failed me as well. Oh, yes, yeah. The cons rule makes progress because it consumes from both sides. So it kind of holds the right-hand side accountable. Whereas this one doesn't make progress. It allows the right-hand side to keep postponing. Yeah, don't worry. I'm your super list. Don't worry about that, right? And keep postponing. So one way to fix this, and yeah, please take it as an exercise, would be to add clocks, right? So you say, you add a tick here. You say, oh, I want to apply this rule only a finite number of times. Consecutively. I mean, you can apply it all the way in the infinite proof, an infinite number of times, but consecutively only a finite number of times, which means that eventually, always eventually nil or cons should appear. So you can, and you can simulate this by adding another argument, let's say an extended natural number with infinity. You can put infinite, and as soon as you apply this cons, you can decrease it to some number. And these cons are, sorry, and this would not be. It would not be feasible to. It would be impossible to apply it indefinitely. Right. I just keep that. This is basically the coinductive way to make sense of this inductive proof. This just follows the pattern that I have explained before. But this is for me. Whenever I do a proof by coinduction, this is really what I do. I build this. I build a proof, an infinite proof tree in my mind, and then I write down the relation. Right. Okay. So one way to fix the another way to fix this is to a bit less intrusive, is to merge these two rules, right? So to say that okay, a finite application of cons R, a finite number application of cons R, together with an application of cons. So I have to make sure that we have progress. So nil, by its nature, has progress, and we want to make sure that we are making progress on actually consuming elements as well. So one way to correct this is to have a rule that is called cons append. And what we are doing, I'm using this for appending a finite list. So we are saying that, yes, either this is nil, or we are going to find some position where this element A holds, because this has to be a sublist. But this may be later, but not indefinitely later. We cannot postpone it indefinitely. So we plug in a finite list here. So we kind of merge a finite number of application of this rule with this rule. Okay? And now this we get something that we still shouldn't take for granted, but we can check that it verifies some alternative, uglier but more certain notion of sublist. Okay. All right. So, what is the difference between induction and coinduction? Abstractly speaking, they are perfectly dual, right? So Nasta-Tarski just dualize, and it has some interesting generalization, the Nasta-Tarski theorem. So it has a categorical generalization where you have a way of building up initial algebras and final coalgebras. So this is perfectly dual if you work in an arbitrary lattice or in an arbitrary category with some completeness and co-completeness properties. So abstractly speaking, they are dual. But concretely, we have this difference here. So induction means whatever can be proved using a finite number of rule applications, and coinduction, whatever can be proved using an infinite number of rule applications. So this kind of justifies this peculiarity of the, let's say, of the instantiation of Nasta-Tarski in the category of predicates over sets. This peculiarity brings this distinction between finite proof trees and infinite proof trees, and finite number of applications and infinite number of applications, which kind of justifies the writing of the rules in a direct fashion for both induction and coinduction. Because you just say, yeah, I think of this, coinductive means I can build infinite proof trees, inductive means I can build finite proof trees. So let me refine this a little bit. One thing that I should say is that, smallest versus largest is kind of like, it's nice mathematics, but finite versus infinite is really the intuition that we are applying when we are doing reasoning. So kind of we are biased towards the category that we work in, which is a form of category of sets. So, can we make this intuition precise? I'm going to give sort of the general, kind of the obvious conclusion that anybody who has followed the rest of my talk would draw in terms of what happens with induction versus coinduction. But just to point out that this is a general phenomenon. So we can talk about rule systems, right? So we have a notion of a rule, which is a pair consisting of a set of hypotheses and a conclusion. So we talk about abstract rule systems. And H, the set of hypotheses, is a finite set. So we are just talking about rules abstractly, right? So we can indicate the rules using graphical notation. And an axiom is a particular case of a rule that has no, like the nil rule, it has no hypothesis. And let's fix a set of rules over some set A. So A is going to consist of the elements, the items on which we are making judgments. So we're defining perhaps a predicate on A. And we can define let's say, the inductive predicate given by the rules by saying that, whenever we have this an application of a rule, if the predicate holds for the hypothesis, then it holds for the conclusion. Okay? And the coinductive predicate defined by the rules has exactly the same direct rules, but it is obviously coinductive. Okay? So this just generalizes what we have discussed. So what is the semantic recipe in this context? We define this functional, we define this operator on predicates, this F, that is the operator associated to the set of rules R. And this is because you have asked about whether this is automatic or not. This is essentially what happens. So this is a general pattern of how you define F. You just say that, yeah, apply to a predicate P, takes an A, and brings all the possible hypotheses that would have led to A, and the predicate held for them. So it's a backwards application of the rules. So F is easily seen to be monotonic. Again, this is a generalization of essentially what we have seen, and we define these predicates as the Nath-Tarski least fixed point and greatest fixed point for R. Okay, so we defined this abstractly for any rule. So this applies in principle to any predicate with just one caveat. We can have higher order predicates as well in the rules, and this slightly complicates matters. But one can show that one can even show that any monotonic operator on a complete lattice is given by a set of rules, such rules. So you can make them all first-order rules. So this covers quite generally the situation that we are talking about. But it does it in a fairly concrete fashion because we can visualize the trees. Unlike in the Nath-Tarski theorem, we have a notion of a rule, and when we have a notion of a rule, we have a notion of a proof tree, right? So we define the data type of proof trees as, well, what's a proof tree? Is a tree whose nodes are labeled with the elements of the set, and such that the successor nodes corresponds to the rules. Okay, so in pretty much in any mainstream proof assistant, you can define this as a data type plus perhaps an invariant. So what we are interested is that each node corresponds to a rule application. The rule application could be an axiom, right? So, which means that the tree ends there. That's an actual leaf. Okay, so it's clear what the notion of an R proof tree is for a set of rules. Okay, and just a bit of terminology. We say that a tree proves an element if the element is the root of the tree. And we define what finiteness means. In this case, we can just say that the set of nodes is finite. So the trees are a priori, they can be infinite, right? So we have, this is an example of an infinite tree. Let's say that these are the rules. Okay, everything is starting to fail me. So anyway, so this is an example of some rules, and this is an example of an infinite proof tree you are built using those rules. So I hope it is clear that we can have infinite proof trees in this context. Nothing stops us from having it. Sorry, what did I do? That was a finite proof tree. Okay, my mind seems to start failing as well. And this is an infinite proof tree. Sorry for the confusion. So this is an infinite proof tree. In this case, you apply the rule shown in blue. You apply it an infinite number of times backwards. And this is essentially I would say the crucial theorem that sort of links the concrete set theory where we are working in with the abstract greatest fixed point stuff. So let's first look at the theorem at the top. So the least fixed point holds. So the predicate defined as a least fixed point holds for an element just in case there exists a finite R proof tree that proves A. And the greatest fixed point holds for an element just in case there exists a possibly infinite R proof tree that proves A. So this is kind of like the ideological theorem that allows one to write the coinduction rules as in the direct fashion as well, and interpret them as infinite, as provable by infinite proof trees. Okay. Now, a final note. before I'm going, I'll go to a quick demo. This is really not. I spent all my time arguing that we're talking about infinite versus finite and so on. It's an important intuition, but this is really not about infinite versus finite. So if we look at the problem more abstractly, we see that induction. For induction, we're talking about finite trees simply because we do not allow infinite depth. There's nothing preventing us from allowing infinite width. So allowing the proof trees to be infinitely branching. That's perfectly fine with respect to induction. So it's not really about infiniteness, but about well-foundedness. So induction is kind of like obtained by restricting coinduction with respect to the depth of the trees, not with respect to necessarily to the width. Infinitely branching in inductive relations or inductive relations defined using infinitely branching proof trees make perfect sense. So really, this is the truly general version of this correspondence theorem. Is the predicate defines as the inductively from the set of rules holds just in case there exists a well-founded proof tree built using those rules. And for the coinductive version of the predicate, there's no such restriction. So in some sense, in this view, the coinductive version looks actually more natural. All right. Okay, so I think this actually concludes my description of what I regard to be the essence of coinduction and induction and the differences and the sort of the set theoretic coincidences between them. I have only covered so-called rule induction and coinduction. The story about is longer and involves sort of let's say categorical generalizations of the lattice theoretic stuff, which gives us the data types and the co-data types, and they come with their own structural induction and coinduction and so on. But I covered a particular kind of inductively and coinductively defined predicates, which are really pervasive and quite useful in theorem proving, but they are not the only ones. And I put here an incomplete list of texts that I found useful, including one of my own, on introducing these concepts. So the paper by Paulson is actually done in Zermelo-Frankel, so it is in a richer set theory, but it explains very nicely this semantic approach. Benjamin Pierce's classic book also has a section where it explains these things very well. I think it introduces this terminology about consistency. There are also discussions in the context of dependent type theory. So Chipala's chapter on coinduction, which is formalized in Koch, actually has some revealing explanations, and so does Berthaud's tutorial on coinduction. What we did in this paper, Witnessing Codata Types, we actually illustrate the use of rule induction and coinduction in Isabelle in order to prove an abstract result about the completeness of data types. And there's this paper by Cozen and Silva, which is explaining these things very well. All right, so I think I'm going to move to the final part of my tutorial. I'm happy to take some questions now. I just want to show a quick demo to see how these things look like in Isabelle. So this would be the yes, Gary.
Coinductive proof is infinite. How can you write a finite proof in Isabelle?
Yes, I mean in the same way you write a blueprint of the. So if you are a Platonist and you think that no, that is the proof, that infinite item, that's the way I prove. You have to buy this kind of like a little bit this meta argument that says, well, a proof by coinduction, exhibiting a coinduction relation, that indicates that the Platonic object which you have in mind, which is an infinite proof tree, exists. But we buy this kind of meta-arguments all the time in the context of induction as well.
So finitely generated would be that.
Yeah. Finitely generated. Yeah, in the sense that from a finite blueprint, from a finite pattern. Yeah. But that's a good question, because that's essentially what I have been struggling with motivating the coinduction proof method. Yeah. I would say that it's not immediate. I mean, I would not just nod at it before I see the infinite proof tree. So only when I see the connection with the proof tree, I accept it as a valid proof method about infinite objects. Okay, so let me show you how these things look like in Isabelle. This is going to probably take about 15 minutes, and then I'm done. Jamie, I think now I will need you around, please. But I don't know how to make this thing. Okay. Thanks. Okay, so just to show you how this last result, this characterization theorem, looks like in Isabelle. Doing type decals and cons is not necessarily best practice, so there are better ways to do this, but ignore this if you are an Isabelle expert. So we have this set. We have this set A that is fixed as a type, and I fix this set of rules. In this case, I'm using lists for the set of hypotheses. So I kind of do not. Currently I am not practicing what I preach. I'm not staying at the level of abstraction from the informal description where I'm using finite sets. But this is possible. So I'm now using lists of hypotheses. And this is the inductive definition of the relation that is given by those rules, right? So everything that is given by a well-founded application of these rules, which in this case, because the relation is finitely branching, in this case it also means finite, but not a priori finite. Okay, so you see what happens here. For those who haven't seen Isabelle before, I'm writing this. Perhaps this is not the best first example that you should see in Isabelle. It looks fairly abstract, but it's just one rule, right? This is just one in the inductive definition that contains only one rule. Whereas the base case, well, if some of these rules are axioms, do not contain hypotheses, then this yields a base case, right? So this rule has base cases, even though it does not necessarily show. So what happens is that that is a user specification. That is not initially a definition, right? The user just writes the rules for the to be inductive predicate, and Isabelle proves various things. So proves monotonicity, and then proves the introduction rule, the elimination rules, and the induction rule. So it does this, what I showed on the slides. It does these proofs in the background, and it looks that it's happy, so it means that it managed to prove this was the bottleneck, right? It managed to prove the monotonicity rule. And everything else is routine, is unlikely to fail. So now it has proved all the necessary properties. And it just announced us, it told us what it proved. And the same thing for coinductive. So this has the same, in this case, it has the same definition. It's just that we have the co part. Notice again that we are talking about these two variants correspond to each other, an inductive definition versus a coinductive definition. They correspond to each other in the sense that the coinductive definition allows for infinite proofs, as we discussed. It doesn't mean that we apply this thing just blindly to lift concepts from finite to infinite. We have seen that this kind of thing, so the IR that we used for finite sublists will not give this JR for infinite sublists. Okay, so it's not to be. But here we're just talking abstractly about things obtained, things proved using finite proof trees versus infinite proof trees. Okay, so how do we describe the proof trees now? We have this thing, and I haven't actually gotten into that. This is one area that was not covered by the tutorial. We have these things called a co-data type or a coinductive data type, and several, not too many, but several theorem provers, proof assistants support coinductive data types as well. And as you can probably infer by analogy with the rule induction stuff that I have just discussed, the difference between an inductive data type and a coinductive data type is that for the coinductive data type, you allow for the infinite application of the constructors. So for example, streams or lazy lists can be defined as a coinductive data type. Here, as a coinductive data type, I'm defining the proof trees. So by default, I'm allowing them to be infinite. If I want induction, I can either do data type instead of co-data type, or I can add an invariant that forces, not invariant, but cut with a predicate that forces the trees to be finite. Here, I'm focusing on the coinductive characterization. So I ignore the inductive part. So I'm going to ignore the IR. So far, this coinductive data type tree has one constructor called capital tree. And this is applied recursively to a list of trees. The syntax over there says that we also have a root that is an element of the type A, and we call it a root. So we give a name for the destructor. This is called the root. Now, these are just blind trees that just put together the elements of A, right? And they are rows trees, so they are branching in undetermined but finite successors. We want to say that at each moment, at each point in the tree, the trees are correct with respect to the rule applications. Right? So we want to traverse this tree, and we want at each point in the tree that there exists a rule that such that the hypothesis yield the conclusion. Right? So we want them to be correct proof trees. And this is another use case of a coinductive predicate. It is a bit of a chicken and egg problem. I mean, I'm not trying to bootstrap now what coinduction is, so I'm using heavily both co-data types, which are fancier than coinduction, and coinduction in order to show the proof in Isabelle of this foundational theorem about coinduction. Okay, so don't think about like bootstrapping here. So the natural thing to do here, in order to say that a possibly infinite proof tree, possibly infinite tree is a correct proof tree, is to do a coinductive definition. And what the coinductive definition says? Well, it says that this is a correct, P tree is a predicate that says it's a correct proof tree. So a tree that has these subtrees, TS, and root A is a correct proof tree if mapping the roots of the subtrees together with the root of our tree, which is the conclusion, it is actually a valid rule. So there has been a valid rule that has been applied at that node. And coinductively, we know that each of the subtrees, the way we quantify over all the subtrees, we just take all the elements that appear in the list TS. Each of the subtrees, for each of the subtrees, this predicate holds coinductively. Okay. Let me ignore this finiteness. We also have this F3, this finiteness condition, which is used for data types. Actually, I will not ignore it. So I promise to ignore the inductive bit, but I'm going to go through it as well quickly. So now we have a predicate that says that the tree is finite. How do we define that a possibly infinite tree is finite? This requires an inductive definition, not a coinductive definition. We do want to apply a finite number of rules before deciding finiteness, right? So we want to say, yeah, this is finite, and if this is finite, and this is finite by applying the rules, and we want to be able to stop. So the notion of being a correct proof tree, again, thinking about the universe of possibly infinite trees, the notion of being a correct proof tree is an example of a coinductive predicate, and the notion of being a finite proof tree is an example of an inductive predicate. Okay, and they have different intuitions. For the coinductive predicates, again, we think backwards, and for the inductive predicates, we typically think forwards. And finite, by the way, finiteness is deceptively simple. It looks like it almost doesn't say anything, right? So it says that if all the subtrees are finite, then our tree is finite. But the fact that it's an inductive interpretation means that it's going to stop at some point. So it actually captures only those inductive, only those finite trees. Okay, and then there is the proof of why this least fixed point IR coincides with the existence of a finite proof tree that has it as a root. And as you would expect, the proof goes by induction on the definition of IR. Okay, so we induct on the definition of IR using the least fixed point predicate, and we are building the tree inductively. So we produce this existential. Okay. I will spare you of the details. We actually need a bounded choice axiom here in order to actually get the roots of the tree to get the actual trees, to get some concrete trees that would correspond to the proofs, and they form the subtree of the tree that we are going to build. Also, for some of you who may not be familiar with proof assistance or with Isabelle in particular, notice that we have this dual screen here, right? So we have upstairs are this is a proof script that I write, and ideally it should be a readable proof script. I can choose the amount of detail that I put in there, but that's something that, to some extent, it is a standalone document. This looks a bit like a structure proof that a mathematician will write. And downstairs here, I have the actual state, the low-level state that is manipulated by the system, by Isabelle. And it shows me what I have to prove and so on. And I keep an eye, basically I edit this document from upstairs while keeping an eye on the state from downstairs that tells me where I am and whether Isabelle is happy with what I've done or not. Okay, so for the inverse relation, for the inverse implication, namely assuming that we have a finite tree, is it the case, a finite tree that proves that element, so it has that element at the root, is it the case that the inductively defined relation holds for it? So it is in the least fixed point. And here we are doing induction on the tree. So this is structural induction on the definition of, sorry, not structural induction. This is actually induction on the definition of finite tree. So this proves the inverse implication. Isabelle has this, another thing to notice here, sort of a side note. There are these facilities that allow you to be succinct and yet informative. So it allows you, for example, to do induction on some variable while keeping another variable arbitrary, which means that we are talking about the universal quantification generalization over the indicated variable. And it also matching standard mathematical practice, it allows you to name the cases. So when you're doing a pen and paper proof, you say, oh, okay, I'm going to prove this by induction. In the case of the nil rule, I have this. In the case of the cons rule, I have this. So Isabelle mirrors this in this This is the structured ISAR language that stays sort of on top of the raw part of Isabelle. And this allows you to write these things in a structured fashion. Anyway, so long story short, this is the opposite implication, and it's proved by induction on the definition of finite tree. And then we have this theorem for the inductive data type. We have that if A is in the least fixed point, so in the predicate that defined by the rules as a least fixed point, then it is provable by a finite proof tree. If and only if, sorry, it is provable by a finite proof tree. Okay, and provable means there exists a proof tree that has it as a root. Okay, finally, for the coinductive part, how do we prove that if there exists a proof tree for A, then A is the greatest fixed point? We are doing coinduction on the greatest fixed point definition of JR, right? Of this greatest fixed point predicate, and we take advantage of the fact that the trees are backward closed under the rules. So the proof is pretty immediate. It's actually simpler than in the induction world.
What's the JR code? What is that?
This is the coinductive proof method associated to JR.
So that's automatically generated every time you declare JR to be coinductive?
Yes. So essentially, what happens is exactly what is on the slides. So I define JR coinductively, which means that those theorems, including direct rules, case distinction, and coinduction, they were generated. And now this is actually being applied.
Oh,
so it's
part of that on the three rules, on three or four rules.
yeah. So let me just. I'm not that skilled with this laptop. That's unfortunate. Control C. That's a Windows one. Yeah. So we can show this theorem. It's an actual theorem. So this says that JR this is a coinduction rule for JR. If some predicate X is backward closed, is like consistent with the rules, then it is included in JR. So remember that this is formulated as an elimination rule. So you know that X holds for X, and you want to prove that JR holds for X. And in order for this to happen, you want that the case distinction rule applies to X, to capital X, the predicate capital X. The choice of the variables is not ideal in this generated theorem. Okay, makes sense? And that's the coinduct, that's what it does. It just applies this as an elimination rule. But does some nicer things because it allows you to name the case and so on. So there's some friendliness there going on beyond the raw application of the elimination rule. Okay? Now, this was quite nice and easy, proving that if there exists a tree, then JR holds. So then the coinductively defined predicate holds. But how about the opposite? And with this, I promise to finish. So how about the opposite? So let's say we want to prove that if JR holds, then there exists a tree. Okay, so this is a bit contrived. So let's just think about let's just look at the bottom theorem, and how do we prove that if the left-to-right implication of the bottom theorem? How do we prove that if JR holds for A, so if the predicate holds for A, then there exists a tree? In the inductive world, it is okay because it is fairly intuitive what we should do because we can build the tree incrementally. Right? How do we show that there exists a tree? Well, by the induction hypothesis, there exist these trees, and now we have the rule, and we add one layer, right? So we get the bigger tree. But here, how do we build this tree? We don't have this a priori incremental way to build a tree. We need to produce, in this kind of context, it gets a bit technically a bit more complex, because we need to produce the whole tree. So knowing that we have an element, and knowing that we are in the greatest fixed point, we want to produce an entire tree that is a proof tree for it. So we do go through it and produce this incrementally, but we cannot just say there exists and prove an existential by some form of induction or coinduction. But we need to bring another piece from the arsenal, which I haven't discussed, which is also an exciting area of research. This is called corecursion. So I show some examples of corecursive definitions on streams, but I haven't discussed them in the tutorial. So this is what we need here. We want to produce the tree corecursively. We don't have.
Just behind you in the.
Thanks. I guess I'm not going to use green.
It's fairly white.
Okay. So we know this, that JR of A holds, and we want to show that there exists a tree such that T essentially proves A, right? So we want a tree, possibly infinite, that has A at the root, so it proves it. How do we do it? This is the greatest. The greatest postfix point. In particular, it is a postfix point. So there must have been a rule and some hypothesis, right? Let's say a rule of the form H, from H we deduce A. So let's say from A1, AN, by some rule we have deduced A, such that JR of A1 and JR of AN holds. So we take advantage of the fact that this greatest fixed point is consistent with the rules. So we start building our tree here. So we're going to put A1 here, A2 here, and AN here. And we make our way backwards. Now we keep applying the same property here, and our tree grows. Okay, and it possibly grows indefinitely. So the intuition is pretty clear. But the problem is that, I mean, the fact that what makes things technically more kind of feeling unnecessarily complicated is that we cannot do this reasoning incrementally, but we need to come up with the whole tree at once. And for this, we have to do a corecursive definition. So we have to provide the witness the entire infinite object. So this is the purpose of doing a coinductive definition, which is called getTree here, which actually produces this infinite object that I'm talking about. So this is a case where you have to just plug in the witness. Whenever you have to prove the existence of an infinite object, there's no other way but to do corecursion. So what you have to do, you have to choose some hypothesis. So given some element A, you have a function that chooses some hypothesis and applies this hypothesis corecursively, and we have this corecursive definition called getTree, and this is a function from our set of elements A to the set of possibly infinite trees. And what it does, it applies the constructor, and then corecursively, notice that getTree calls itself corecursively, and it does it through a map function. This is the natural corecursive style of definition for trees. This map function is the list map, right? Because you want to map over the list of subtrees. So this is essentially primitive corecursion. For streams, when I'll show you those examples with functions defined on streams, this map is actually hidden by the fact that it's trivial. It's a very simple map. It's just pairs there. But for corecursion, you are applying the map of whatever nested data type you are using inside. Anyway, long story short, this is the only sort of a bit more technically involved part of the proof, because we need to provide directly a witness. We need to provide the infinite tree directly, as opposed to just proving an existential. So once we have defined it co-recursively, the coinduction would take advantage of its property and would work. So the final implication is actually proved by coinduction on the definition of proof tree. Anyway, so I hope this demo was not terribly chaotic and confusing. This ends my tutorial. Thanks much again for your patience. I'm happy to take any questions. Yeah.
So that sum keyword, is that it picks like a set of hypotheses that we
Yeah.
So what if you had a non-deterministic set of rules? There were multiple ways of proving A.
This it just picks one. It's sufficient to pick one rule and one set of items that matches the rule. No, because the property is fairly unspecific. We just want that there exists a proof tree. And this sum, really doesn't know anything. It's a specificity of higher order logic that I think takes many people away from higher order logic for not such a good reason, in my opinion. But the sum is some element that satisfies the property, and we don't know anything about it. But in some cases, we want to build some specific trees, and then we can get more refined. Yeah, for this, sum was good enough. Yeah. Yeah.
I don't know, question. Is there any connection between this approach and using push-down automata?
I mean, you mean like the coinductive part or the inductive part?
So you wanted to prove that. So there are approaches for the. So there is this study around decidability of push-down automata, and you're trying to make this, inductive rules and coinductive rules. So you can just design everything as a transition system.
Yeah. So I mean, this doesn't touch on decidability issues and so on, but it can probably be fruitfully combined. I know that Damien Pu is actually doing a lot of stuff with this. So he has some decidability results for regular languages that he obtained with coinduction and coinduction up to and these kind of things. And I'm not entirely certain, but I think I saw some extensions to push down automata of this work. So, but it's by itself is not tackling this. Those are two specific things: the decidability aspects and so on. But the final automata and final construction and so on are sort of directly related to final coalgebras and greatest fixed points. I mean, they kind of inspired those concepts. So if you talk to, I don't know, Jan Rutten, for example, he always gives these examples, and his early papers always connect with this final automata for regular languages and beyond. Yeah, but something more specific, I don't know. All right. Yeah, so I'm happy to take any other questions later. So again, thanks much for being patient.